Let's look at proposition 8 of book 3 of Euclid's Elements. Given a circle and a point D outside and various points on the circle, okay, where one of them forms a diameter with D. Okay, let's see. So here we have a line passing through M and D. Let's mark this point of intersection as A, and let's join these two segments A and D so that I can hide the line. So AD is a line which passes through the diameter. Now let's also have some points on the circle, on the concave surface. If I put it here, it would become convex from the perspective of D. Now let's join these ED, FD and CD. The proposition says that FD is smaller than ED and CD is smaller than FD. And of course, AD is the largest. Okay, so if we have to put it in terms of our expression, so this is what it would be. DA is greater than DE, which is greater than DF, which is greater than DC. That is one part of the proposition. Another part of the proposition says that the points or lines falling on the convex surface from D, since anyhow these lines are falling up to here on this, intersecting with the circle on the convex surface. So let's mark those points instead of creating another set of points. So what the propositions continues with is that DG is less than KD or DK, which is less than DL, which is in turn less than DH. Now, the next part of the proposition says there can be, say for example, with respect to K, there can be only one other point on the circle which will be equal to DK when it is joined to D. Okay, let's take it one by one. So let's take the first part. DA is greater than DE is greater than DF is greater than DC. Okay, so let's join these points to the center. So let's join, and since we are focusing on the concave part of the circle, let me highlight it with green. Okay, let's join EM, let's join FM, let's join CM. Now AM is equal to EM, MD is, we can add MD to both of them, so we get AM plus MD is equal to EM plus MD, but EM plus MD is greater than ED. Remember, the sum of any two sides is greater than the third side. So EM plus MD is greater than ED. And since AM plus MD is equal to EM plus MD, we can say AM plus MD is greater than ED. Yes? Again, same logic. FM plus MD is equal to EM plus MD. Because this is the radii of the same circle, MD is same for both of them. So they will be equal. And here again, angle EMD is greater than angle FMD. So it will, subtend a greater side. So ED will be greater than FD. Same way, FM plus MD is equal to CM plus MD, but angle FMD is greater than CMD. So that means FD is going to be greater than CD. So we have shown that DA is the greatest, which is greater than DE, which is greater than DF, and which is in turn greater than BC. So that was our first part. Now let's look at the second part. So now we are going to look at the concave part. So let me highlight that in blue. So now let's join HLK with the center. Now here mg is equal to mk. So now since mg is equal to mk and mk plus kd is greater than mg plus gd, and these two are equal, mk and mg are equal. So that means the remainders dk would be greater than dg. Look at this triangle MLD and triangle MKD. Now MKD is inside this triangle MLD. That means, and the base is MD. So that means the other two sides MK and KD would be less than ML and DL. So that means KD is less than DL. Same logic. In triangle MHD, inside it you have MLD triangle, which means the sides are going to be less than these two sides. So that means DL would be less than DH. So which means we have shown that DG is the smallest, DG is less than DK, which is in turn less than DL, which is in turn less than DH. So both of these two statements we have proved. Now let's prove the third part, which says that with respect to K, there can be only one point on the other side of this diameter where if we join that point to D, then that point and D would be equal to DK. Okay, let's see how we can prove this. Okay, let's do one thing. Let's hide off all these things that are not relevant for us at this point. Okay, so what we are going to do is we are going to copy this angle KMG here at M. If we join the center with the leg of that copied angle. So here the claim is that this is the only point where dB would be equal to dk. At no other point will this be possible. Okay, let's join D and B. Now once we join D and B, you notice these two triangles. MK is equal to MB, radii of the same circle. MD is common to both the triangles, and this angle GMB is equal to KMG. So using side angle side, we can say that these two triangles are congruent. And since they are congruent, we can say DK is equal to DB. Now let's prove that B is the only other point that is possible. And let us say there is a point where dN would be equal to dk. Let's say that is the, so let's join this. Now we are saying that dN is equal to dk, but we know dk is equal to dB, which means dB is equal to dN. But remember, in the previous part, we have already shown that dG is the smallest, dB is greater than dG, and if we join MN, then in the triangle MND, inside that you will have MBD triangle. So that means DN cannot be equal to BD, which means we have reached a contradiction. So which means that there cannot exist a point N. There can be only one point on the circle B where dB will be equal to dk. So dn is not, or rather the point n is not possible. So we have proved it by contradiction. So that was proposition 8 of book 3 of Euclid's Elements. Again, let me remind you that there is a link to a PDF book which describes all these propositions. Please feel free to download it, refer to it. If you feel somebody will benefit from it, please do share it. And most importantly, if you find a mistake, please put in the comments so that I can rectify it. You can always get the latest version of the book from the link provided in the title page of the book itself. That's it for now.